Hi everyone. Today we are happy to have Shuchen to present her work on hierarchical representational learning. So I met Shuchen at NeurIPS 2022, and she and her lab are doing really interesting work on how to extract some biological, psychological insights into making better representational systems. So without further ado, I shall let Shuchen give us the rest of today's presentation. Shuchen, please.
Yeah, so hi everyone. Really happy to be here. So today I will talk about like a cognition-inspired algorithm that tries to learn representations from sequential data. And yeah, so it's called learning structure from the ground up, in the sense that that you do not assume there is an underlying structure in the data and then try to learn the representation in a data-driven way. And you get like a nested hierarchical representation, and the process on how to get this hierarchical representation is inspired by chunking, which you will know if you don't. So let me just to give you an idea what chunking is. Let me just ask you to do this like very simple task. So you read this this sequence, and then if I make this, so like take a second to read the sequence through, and now I make the sequence disappear. And I can ask you, like, what do you remember about the sequence? Anybody wants to try it?
Yeah, I only remember it starts with D, and there's a lot of JK inside the sequence.
Yeah, great. So wait, there's something else in the chat. How do I get to chat? Oh, well, yes, so you actually remember the whole thing. But actually what I want to say is if the sequence is too long for you to remember, you probably remember, it's just like John did, there are a couple of like DFs and JKs in the sequence. So
Wait, so you get the whole sequence, right?
I'm not sure, but it looks like so.
Well, that can be a memory champion. That's a lot of letters.
Yeah. So just by reading the sequence, you quickly notify that there are a couple of DFs and JKs, and then in your previous experience, like DFs and JKs are just random letters, and you don't really associate with like any word, but just by there are DFs and JKs occurring quite often in the sequence, then you can identify like these quite oftenly occurring consecutive units as chunks. So this is a process called chunking, basically identifying consecutive reoccurring units, like if there are like consecutive units that keeps reoccurring in sequences, then you would identify the several units and then group them as a whole. So I learned when I started my PhD that chunking is quite an ubiquitous learning phenomenon. So it spans in language, vision, and action. So so in language, like you often use phrases such as like, as you might know, and then it's different from like the difference between like not chunking it and chunking it is like you sort of remember these sub phrases as a unit, And then studies have shown that like people can store in their short-term memory, instead of like 4 letters or 4 phrases, they can store 4 chunks. So it's like in language there are these bits and pieces that we sort of when we say it, then the whole thing comes out as a unit. And chunking is also a phenomenon in vision, although it's a bit I would say less salient to discover so, but if you see like the visual sensory inputs as like a high dimensional sequential input, so it's like as a baby you have been like, or like growing up you have been exposed to like a lot of like visual information in the sense of like sequential visual information, and then when you have seen things like, oh, there is this thing driving to like moving to the left like a couple of times, then you sort of effortlessly identify like this thing, like this entire thing as an object, instead of oh, like these pixels are grouped together as a unit, but the entire object. And similarly, you may group like this building as another object. And the benefits of like grouping reoccurring patterns together in vision is that it gives you this sense that there are like objects and in the world, and once you can identify objects, then you can also learn how are objects related. So one thing chunking helps with vision is that it helps us to perceive the world in terms of objects and the relations between objects. Chunking is quite also like a pronounced phenomenon in action. So many people read books about habits, and then it's like habits are also something that we just do it so effortlessly. Like when you make a tea, then it's actually an elaborate process. You're not like born and you know how to make tea, but this process of like opening a tea bag, like putting the tea bag in the bowl, and then like putting some water and wait for 1 minute and then drink it. It's quite an elaborate process, but somehow like for people around our age, you just do it without even thinking. But it's a very challenging task for a child, for example. And then we benefit from this kind of effortlessly doing this process by sort of like chunking these actions together into action sequences, and then these action sequences we can execute without thinking, and it's like so why is this such habits beneficial? For example, when you imagine like doing planning, such as going from here to Singapore, or like I need to finish this project in like a month, then you can sort of imagine what is going to happen in the units of chunks, and thereby you just need to think about, okay, how to plan these modularized structure instead of like these simple granular units. And then when you make a tea, you don't think about how to put the tea bag in the pots, but you do this entire thing together. So in cognitive science, people have suggested that chunking facilitates memory compression, like storing several chunks in your short-term memory can enables you to remember longer sequences. And it helps with compositional generalization, as when we go like when we know about how things are related in one place, and if we go to a novel place, then we can transfer some of our knowledge. It helps us to predict what is upcoming in the future based on like the previous structures and the relations between the structures we have acquired, and communication. Like when we talk about like ideas or items with like ideas with each other, then if we have like a common underlying chunk representation, then we can also use like one word or one concept to denote what we're talking about. So so I started my PhD, stumbled upon this really interesting phenomenon. And then one striking thing to me is like it doesn't resemble like the machine learning or like how neural network works, right? So yeah, so I was really curious because I'm really interested in how we arrive at structured representation of the world. And then I think structured representation is something that is not yet explicitly represented by neural networks. So I was wondering like how to study this kind of process, how to come up with a model for it, and then what are and how to evaluate such models.
Yeah.
So
Shuchen, if you don't mind, I got something to ask.
yeah, sure.
So actually, I got
Please.
two questions. The first is like in all this like language, vision, action domains, how do you know what's the smallest unit to chunk on? Like because there's so many different things. Like for the teacup, the tea, the water. Like what's the smallest unit? Like, do you have any idea? That's the first one. And then the second question I have is like for word embeddings, like large language models, are they considered a kind of chunk, or is it like latent space? Is there a difference between like latent space and chunking? Yeah. So yeah, these are the two questions.
So the first one, what is the minimal granularity? I guess if you're asking about what is the minimal granularity as represented in like these biological systems, although I don't really know about this, like I can't give you the correct answer for sure. But I think, for example, in like if you look at like the neural representation, and if in fact like if information is represented in neural activities, then the granularity can be like a set of neural firing patterns. Just it could be my hypothesis. Is it like something that you're wondering about, or?
Yeah, so actually the set of neural firing patterns is probably independent of the input, right? So it just depends on where it's mapped to, which perception is mapped to. Like if it maps to the eyes, then it will become like visual chunking. If it mapped to maybe like, I guess, sequence of actions is probably some temporal sequential thing in the brain, like something that processes temporal sequences. Yeah, maybe memory. Yeah, yeah. So you're saying that the chunking phenomena is independent of the senses. Is that roughly what I'm getting?
Yes, that's yeah, like you see documentations about this phenomenon in multiple senses. Like expert chess players identify constellations of strategic board positions at like in one unit, and they can like they even remember like these board constellations compared to like novel chess players. Yeah, it's spanned upon multiple sensory domains, and this is something quite super fascinating about it, because then you start to wonder, okay, is it because there is like a common underlying neural computational principle that governs almost all perceptual domains?
I thought it's more related to the concept, because I think so when I first asked the question, like it's very context specific, right? He asked about the vision, language, and action. So I thought like it's more intuitive if you think this problem from like a conceptual perspective. For example, in vision, then it's like, for example, when we do image segmentation, like what level, based on what level of granularity you want to segmentize the image, right? So for example, the example you gave here, I think if I understand correctly, so we treat one, like for example, we treat a building as one entity, we treat one vehicle as one entity, and we treat the ground as one entity. But it really depends on how granular you want to go, right? You definitely can go even into more the finer details. For example, how do you segmentize the building into the bricks, the walls, the doors,
yeah,
the
you mean
windows,
like,
right?
for example, if you are asking for someone for direction, then you want to like segment out the bus driver from the bus, and it's
Right.
like it's task dependent.
Yeah, that's what I thought. It's very task dependent, and in terms of the what's the most basic, most granular level, I think it really depends on, can we conceptualize that concept? For example, I really want to go into molecular level, but it's not helpful in this use case, right? Yeah. So I think it's the same. It's the same for action. For example, this T, when you want to make a T, right? Then I mean, we definitely can go into how your muscle contract and expand and stuff, right? But I think it's appropriate to just stay as how, maybe if you think from how we actually make a roll, all the motor moves, that becomes the most granular level of the chunking, I think. So we don't need to really go to even more detail than that. Yeah, that's my my take on this question.
Yeah, so so my take is, it's like depending on the task and context, maybe you want to have different granular representation, but in either, like in any type of granular representation, you like the process of identifying like a certain part of the sensory perception as like an object is quite critical. And then it's like there can be task dependencies, but like to study this to study how this process arises, and it's like then I start simple with how these like object perception arises from sequential data input. And the second question, I forgot the second question already.
Oh yeah, it's about like how related is like chunking compared to like maybe like latent space embeddings, like for example word embeddings. Like can like sort of chunking be used to generate a latent space, or like are the two of them like different?
Word embeddings meaning like the kind of like word to vec embeddings.
Yes, something like that. Yes, like a hidden dimension of like either a larger number of dimensions or smaller number of dimensions to represent like maybe a semantic meaning of maybe a word or some other object.
I think they're related, but I think they're not exactly the same. But I've been very curious about like, or yeah, I'm planning a project to try to figure out what can be the relations. So I
think on that, the second question, I feel like it really depends on how your embedding is trained, right? Are you training the token? Are you tokenize the sentence, the word, or the individual characters? So that's how you chunk, right? How you tokenize is how you chunk.
Yeah.
So I actually I have this thing which I've been thinking about, which is like the like nature versus nurture. So like I think chunking is more like nature kind of thing. Like it is sort of like some biological rules that is present to help us to learn or to effectively group things together. Or like maybe semantic meaning might be learned. Yeah, so somehow if you can map the two of them together, you can learn like meanings of like chunks of words. Yeah, but maybe at the fundamental level, the semantic meaning might still need to be learned through experience. but then you can chunk words together after that using some hierarchical rule that is like naturally learned, like you already know this beforehand, like when you were born. Yeah, I have a feeling that like the phenomena of chunking might be already like pre-engineered into us to like how to chunk things together. Yeah, it's just that we probably haven't figured out the rules yet. Yeah, that's why I asked this question. Yeah, and also there's another point of view is that maybe through some means of chunking, you can actually map like a very complex starting object into a simpler representation.
Yeah.
Yeah, so that's another aspect to view it as well.
Yeah. So so that was actually the question that I was thinking really hard about. Is like, if we are so good at like grouping reoccurring things together as a unit, why do we do that? It's like, why do nature or why do evolution put this engineered process inside us, like throughout this like millions of years? Why do we have this facility? I mean, it's not just humans, it's also like, you know, people have shown like monkeys, pigeons, they do chunking as well. So my question was, does it say something about the underlying perceptual data itself? Like, is there some structure inside perceptual data that makes chunking a good strategy to discover like the relations between objects and items in the world? So so I started to answer this question with this like very simple generative model. And this generative model is basically, it contains nested hierarchies. You can sort of think about this generative model as like a extreme cartoonized, simplified representation of how the world may come from. And basically, you use this generative model to generate sequences. And the generative model is composed of, like in this world, only two things matter. The red thing and the green thing. So the white thing is empty, so it's null, or it's no observation. And then basically this like red thing and green thing is called an alphabet set, but it's just like the basic units you start from. And then in this world, like red thing and yellow thing can be like was combined together to like red green as a unit. And then it's like, okay, so it's like the thing red green is created, and red green can also create like a green red as another object. And then this object can also like combine together, like you can combine red green and green red into like red green green red. Like these type of like new objects can be created by recombining existing objects. And then up to 5 objects you can create in this world. So so D basically denotes like new objects you can create by recombining the previously created objects. So for each object, there is a certain probability that this object is going to occur in our and in this sensory sequence. So so the way you generate the sensory sequence is that given this set of objects, you randomly sample an object based on the assigned occurrence probability. And then you concatenate them one after another to become this perceptual sequence. So how does it exactly work? Or like I have a demonstration. So this is like you so you start with like the elementary atoms, and then you generate like combinations of new objects from recombining pre-existing ones, and so on and so forth. And then perceptual sequences are randomly sampled from this set of objects. So that becomes our perceptual sequence. And now this perceptual sequence is given to a learning agent. And then the learning agent has no idea, like, okay, like what is going on in this one-dimensional world, and wants to uncover what is the underlying structure, or like what are the objects that I can use to describe this world. So this is like the hierarchical chunking model is trying to emulate this process, and it's inspired by this Gestalt principle of grouping by proximity. Maybe Gestalt as a word is really scary because it sounds very German. Actually, I think it is German. But what it essentially means is that perception is, so in history, there is this group of psychologists called Gestalt psychologists. And basically what they study is, they assume that we perceive the world based on structures. And then how we arrive at structures is based on the set of Gestalt rules. And so what they have been doing is like coming up with a set of Gestalt rules. And these are rules that we use to arrive at a structured representation. And one of the very pronounced Gestalt rules is grouping by proximity. That is, we tend to group proximally perceived object as a unit. So that's related to chunking as well, right? So I was really excited about this. So basically, yeah, going back to the hierarchical chunking model. So the hierarchical chunking model tries to parse the sequence in units of chunks, and at the end of learning, you want to arrive at this like representation as like the sequence is like a set of chunks, and then the probability of perceiving a sequence is like a factored representation by the chunks in the sequence instead of the individual units. So, so how the learning process executes is, I would say, rather simple. So you have, let's say, you have learned this set of chunks, and then you always use like the set of chunks in this set I denote as B, which is like the belief set. You always use chunks in the belief set to parse the sequence. So it's a bit like things in your memory. And so it's like, okay, previously I can identify a cat. So now if I just see like 500 pixels together that resembles the cat in my memory, then I will identify this 500 pixels as a cat. And then I just need to explain like another 30 pixels of what is happening in this visual field. So you always use a set of chunks to parse the sequence. And then by parsing, in doing so, you would have like an idea about, for example, how frequently each chunk is being parsed in the sequence, and also how often does each chunk transition to any other chunk. And then if there are, for example, this green red chunk keeps transitioning to this red green red chunk, then you group them together as units when it violates an independence test. So then, so thereby, you arrive at your updated belief set, which is like your original belief set, like this part, and this additional chunk that you just created. So that's how a new chunk is being created. And to give you a demonstration on how the learning process looks like, you have the perceptual sequence, and then the hierarchical chunking model build up chunks recursively by merging these previously learned chunk. So you start with the representation with like these atomic units, and gradually these atomic units merge into simple objects or simple chunks, and recursively you can augment the belief set by this violation of independence test. So based on this particular generative model, we have derived a learning guarantee that when the length of the sequence approaches infinity, then this learning process learns a representation that is isomorphic to the generative graph. And the proof is by induction, but it's very dependent on like how this generative model is set up, and then the learning process essentially like picks the chunk that has like the biggest probability mass that violates the independence criteria.
Sorry, I have a question here.
Yeah.
So when you say learn, what do you mean? Like, because my current understanding is the generative, this hierarchical chunking model is generating this sequence. So what do you mean by learn?
No, it's the other way around. So it's like you have a generative model. It's like you cover the eyes of HCM, so the learning model has no idea where this sequence is coming from, and then you have a ground truth generative model you use to generate sequence, and then this sequence so this sequence is generated in this way. So it's like this is how the sequence is being produced, and then this, like, once the sequence is being produced, you don't like then HCM needs to, like, the goal of HCM is to uncover the structure underlying the sequence.
I see. But is it possible that is it guaranteed that the learn, like when you use HCM to learn how to generate this sequence, it always uncover the generation rule according to the ground truth model, or it can learn something else? Because to us it looks quite random. So I'm guessing there might be other ways to generate the same sequence.
So yeah, so in this particular generative model, yeah, it sort of depends on the assumptions, because like in this particular generative model, things are generated like as a bit of like an inverse process of the learning process, but it's like, but in real world there is no way to say that, okay, the underlying ground truth is this generative model, and more likely that the underlying ground truth is something completely different. So in that case, you would learn a representation that does not represent the true ground truth. But in this particular context, it's like if the ground truth is created in like a very specific way, then you can uncover that ground truth.
So I think like one very trivial way to construct the sequence is just to use the most basic units, right? The red, green, and white to construct. But then, is it the task is to try to learn the way to most efficiently construct this, which means that you use the larger chunk possible? Because there's definitely more than one way to reconstruct the sequence.
Yeah, definitely. Yes. So you always use like the biggest chunk possible to parse the sequence. And then as a result, you will end up having like to generate the same length of sequence. If you learn bigger chunks, then you need to parse it in less number of steps. The sequence complexity can be smaller. The evaluation likelihood can be bigger. Yeah, it comes with a set of benefits. Although this algorithm itself is not looking for, like, it's not changing the representation based on a loss function, although it's like you can also adapt it to do so. But here is essentially recursively grouping correlated pre-existing chunks as like one sentence summary of it.
So when you learn, you know what are the chunks, right?
No, you don't.
So I don't. Then
Like,
I can come out with my own arbitrary chunk, right? For example, I say the first half of this sequence is one chunk, the second half is another chunk. If I don't know the ground truth, what are the real chunks? I can just arbitrarily create my own chunks. So how do I learn?
So how chunks are being created are based on like the correlations, which is based on how often you use this chunk to parse the sequence. So it's like if the first half of the sequence and the second half is only used to parse the sequence once, then it's not significant enough for the system to group them together.
I see. So you want some chunks that is very ubiquitous, means like it's very often used to construct, then you can call it a chunk. Otherwise, it's just some. If you just appear one time, then probably it's just some spurious pattern, not really a chunk.
Yeah, exactly.
Actually, can I ask, we are actually trying to learn how to compress this even further, right? That's the main learning that we are doing, right? To learn how to represent something complex into something more compact, more simple, using chunking.
I think it's like it's a byproduct of learning, but like, for example, a compression goal is not the process that is driving the representation change. Like, it's more like the correlation is driving the representation change.
I understand. No, because actually I last time used to do signal processing. So this reminds me a lot of like how you use code words to like represent the code, and then how you use like because they also chunk together like bits, the 0 and 1 bits into different symbols, and then from the symbols you can then like try to represent the code in the least amount of units. Yeah, so it seems to me like the way chunking does this, there's no loss function per se, as in like no entropy loss function like what they normally do in signal processing here, to try to like make sure that the code words are like the least amount of like average length, you know, like Huffman coding, Huffman coding is like,
yes, it is related, but it's not exactly the same, because sometimes it's like I think with this algorithm, it's most of the time you are doing complexity reduction or reducing code length, but it's not learning the minimal or like the optimal code length.
Correct. So this is something I want to point out. I think this is good because stuff like optimizing a metric, like minimizing code length and stuff like that, this kind of metrics are very difficult to like actually learn. Yeah, what's easy to learn is actually stuff that is rule-based. Like basically you already have like maybe maximal occurrence that you chunk together. Like this kind of like chunking rules that you just keep systematically applying, those are actually much faster for learning. And I think that's what you are doing for HCM as well, right? It's a set of statistical rules to determine what chunks together. At least based on some probability matrix that we saw earlier, that cross correlation matrix.
Are you suggesting that, for example, the loss function evaluation is data dependent? It's like you need to evaluate your representation on this set of data to say, is it a good good compression scheme versus this set of rules that are independent from data that you just
I mean, it's
well,
sort of dependent from data, right? Because you use the data to generate the
the
correlation.
frequencies are, yeah, the frequencies and transitions are coming from data.
All right. Now, I just want to make a point here that like a lot of deep learning right now is all like backprop, try to find the best way to like do some like mapping based on like the data to minimize some loss function. And I think this kind of learning can take like very, very long to learn. So like the kind of learning that you have here, like the HCM where you use like certain preset rules, that can still be data dependent, but because you already have preset rules of what you should do when certain things happen, this actually helps the model learn to map much faster. I mean, you can imagine trying to do this without the preset rules and trying to do this like end-to-end using deep learning. I think it will take forever. Yeah, that's my own gut feel.
No, but I thought when you do learning, you don't know the ground truths or the preset rules, right? You are trying to uncover the chunks, right?
Correct. No, so you are learning the preset rules by using the probability information of the data.
But it still, to me, it still sounds like minimizing the entropy, right? Because when you have the optimal chunking, you will minimize the information entropy.
Actually, we looked into this direction before, and then the conclusion is it's like most of the time it's minimizing entropy, but not all the time. So it's not like you it's like trying to come up with a proof that it is always minimizing entropy that didn't work because in some particular sequence distributions, there can be cases that this grouping by correlation is not minimizing entropy.
How about one concrete example?
It's okay. I don't have it in mind, but it's like in most of our experiments, we can show that entropy is reducing. But you can find like if you try to prove it, then you can find like these corner cases that's in this particular, if the sequence is generated in such a particular ways and it's not minimizing entropy anymore. But it's like there can be better systems to minimizing entropy compared to this model.
Yeah, actually, on this topic of entropy, like I would like to just share my personal view on probabilities and entropies. I feel like it's good only if you have discrete entities, because if you know like the calculation of entropy, let me just write this down somewhere. Yeah, so you know, like you want to calculate the entropy, which is like the amount of uncertainty in the system, is actually the sum of your individual sum over i's of your pi log pi. Yeah, so it's like your probabilities for entropy. I think it's a negative also. Yeah, there should be a minus sign here. Yeah, so entropy over here actually works quite well. Like this basically tells you the amount of uncertainty in a distribution. Like it has the most is the most uncertain. Maybe let me just draw this here so that like I think this discussion over here. No, I just want to say something, but this. Just let me just draw this here because I think some people don't know what's entropy. So let me just show like what's entropy. So like in a binary case where you like flip heads and tails, like this is your probability, and then your entropy is actually maximal, which is 1, okay, at this point here, which is 0.5, which means that if let's say you flip a coin and the coin is like heads or tails, only when the coin has a fair chance of landing heads and tails, that you have the most amount of like information you gain by observing the coin itself. Because like if the coin was like always heads or always tails, you know, you already know the outcome without observing the coin flip, which is why the entropy is 0 over here. So in some sense, like if we were to go by entropy to like try to use entropy to minimize, like they call it code word length in like signal processing, I think it's good for signal processing only because it's discrete. Discrete as in this probabilities here are because there's are finite in terms of the number of like elements there are in the sequence. Yeah, so my own gripe with entropy is that the moment you allow it to go into like a very continuous and arbitrary amount of like starting symbols, it doesn't really characterize that well. Yeah, so the point that I have over here is like, because you use a correlation matrix to sort of like group chunks, yeah, how are you going to ensure that like the amount of chunks that you have are not like infinitely many, such that, you know, you won't have a very good gauge of the probabilities behind it? Yeah, I mean, that's in general is my gripe against probability. Is it doesn't scale very well when you have a continuous like or infinite amount of like base units. Yeah.
But here we're talking about a finite sequence, right?
Yeah, correct. But the chunks there can be infinite number of chunks, you see.
But you generate how? The ground truth must be finite.
I mean the combinatory, because you combine like ground truth chunks together, you can have like chunks that are more like longer, and the amount of chunks that are longer can be there can be a lot of different possibilities.
So if you have learned the ground truth and then use the ground truth chunks to parse the sequence, then there will no longer be a correlation present. So the sequence structure also determines the level of chunks you can learn from this set of sequence. It's like when you use a set of chunks that no longer has a correlation, then the learning process will stop.
Yeah, no, maybe you can go back to the diagram of the correlation. Yeah, I think that's because this is actually not like it's not specific to your model itself. It's more like anything that uses probabilities. We kind of need to kind of ensure that it is actually we kind of need to ensure that it doesn't have too many like discrete ground truth units. Like basically the amount of units here should be like finitely many. Yeah. So like how can we ensure that there will be finitely many chunks to compare with? Because like as you increase the number of chunks, you know, you can actually have a lot of different things to compare with.
You mean the parse process, or you mean the transition matrix itself, like the size of the transition
correct.
matrix?
Because this one can actually explode exponentially in terms of like if you have B chunks, you need to compare B squared amount of terms.
Not necessarily, because if this transition matrix is sparse, then you just need to encode the transition that actually.
Sorry, say again.
So it's like many times it can be the case that like this guy just transitioned to this guy and then transitions to nothing else. So then to represent this transition matrix, then you just need to like encode like a link from this node to the other node.
Yeah, actually I like the idea. No, but you see in the end you create a mega chunk here, right?
Yeah.
That you will then use for the next step of processing again.
Exactly.
Over here. So your matrix will only get bigger, right? You will get a larger and larger.
Yeah, it will only get bigger.
Correct. So then that's my concern here, because like as I said, probabilities work well if let's say you have like finitely many chunks. So I guess you put a cap to the number of times you do this, right? Because if not, you have a lot of.
But I think it won't grow infinitely, because at some point, if you lost the correlation, so the learning will stop.
Yeah, exactly.
Okay, yeah, then it's fine. Yeah, because after a while, you will not need to add any more new chunks, right?
Yes.
And also, sorry, just to interrupt. I think also I know the intuition behind why it doesn't minimize the information entry. It's because now we are just trying to uncover the what's a ground truth chunk you use to construct this sequence, right? But it's not guaranteed that those ground truths will construct this sequence. You are using the optimal chunks. So you are just trying to uncover what chunks you use through this correlation. But that's why it doesn't guarantee to minimize the entropy. There's another way to come up with a new set of chunks to minimize the entropy. But that's not what I'm doing here. We're just trying to uncover the what chunks you use. Yeah, so I think I get it now.
Yes, because it's like if this algorithm is trying to uncover a particular way of generating the sequence, then this generative model is not necessarily the minimal compression way to generate the sequence. And yeah, and then that's basically the reason it's yeah, it doesn't, it like most of the time it's doing compression, but not all the time. Yeah, so what do I have next?
Yeah, I guess
Oh,
we can move on. Yeah, this actually answered most of the questions I had already. Yeah, thanks.
yeah, and then there was a reason I think I didn't really want this algorithm to do information compression, and that was like partially what I want to use this algorithm for is to sort of compare human behavior with this what the chunks it learns, and then I don't think humans are finding the minimal code length or like are trying to minimize information compression, but rather it's like the set of representations we learn are quite redundant and overlapping with each other over time. So yeah, that was another gut feeling that I feel like I don't really want to minimize compression, for example.
I think I can agree with that, because in the reality, the basic set of chunks we use may not always be optimal. Many times it's suboptimal. So if you just minimize the entropy, it may not arrive. It may arrive at some efficient representation, but maybe it's not the real chunk we use in reality. So I think I can agree with that.
Yeah, exactly. And also with regard to the proliferation of the number of chunks in the representation, you can impose some forgetting schemes so that that like basically deletes chunks when it is not being used. And then I think that is related to like why forgetting is useful, in the sense that if you forget about things, then it helps you to have like a smaller set of representation that you can like adapt to in a new environment. So you can impose this forgetting scheme to reduce down the set of chunks. But yeah, most of the time I don't use forgetting.
Another reason I can think of, because it kind of reminds me of my own working. So if let's say in reality you have new sequence, right? If you want to minimize the entropy for your original sequence and your new sequence, you might arrive at different chunks because you're just trying to minimize the entropy. But so which means that every time you have new data, right, you need to relearn all your chunks, that which is not efficient. So you better stay with your existing chunks. Then when you have new data, you want to utilize your existing chunks. So in that sense, it's more efficient. It's more like efficient in the sense that you can recycle your existing knowledge. But if you always want to minimize your information entropy, then every time you have new data, you need to relearn from scratch. So in a sense, it's not efficient.
Yeah, actually, I agree with that point of view, because like in like my memory structure system as well, memory actually helps to give some like prior learning already to a new environment. But if your new environment doesn't match, what you should do is you then should learn the new memory of the new environment and forget all those that clash with the new ones. And in that sense, I don't think humans can ever be optimal, because we are always adapting to our environment. And if you want to be optimal, you probably will die before you can be optimal because there's just so many things changing in the environment. So yeah, I mean, all these information theory constructs are really based on an unchanging environment where, you just need to transmit the same kind of messages in a very like fixed environment. Yeah, but yours, I think, can be used to do adaptable learning also. If you put the forgetting mechanism in here, you can use this set of chunks for a new domain or like a similar domain, but different like ground truth. And then you can like relearn the chunks again. Yeah, so that's why I like it.
Yeah, I haven't thought about this compression scheme in terms of transfer, but that's a really interesting point. But for the sake of time, I think I will move on from here. So, oops, demos. I shouldn't have encoded, I shouldn't have used the GIF to represent it. Now I need to wait when I switch slides. Yeah, so one thing like one experiment we did is comparing this model to a simple recurrent neural network. I think it's like a LSTM. When RNN, like to make RNN and HCM learn sequences that contains this underlying generative hierarchy. And basically, we use the generative model to generate a random ground truth, like graphs, and then evaluate HCM and RNN on their learning performance, how good they learn the representation as compared to the ground truth, and compare like their training efficiency. And then it's like when the number of recombinations increases in the graph, so D equals to 8 means like there are 8 different chunks being created in the generative model. Then there is like a bigger advantage, like learning advantage for HCM compared to like a recurrent neural network. So it seems to be more data efficient when your sequence contains an underlying hierarchical representational structure.
Can you explain this KL divergence metric here? Like, is higher is better, is it, for this? Oh, sorry, lower is better.
Better, yeah.
But what exactly is it measuring? What KL distribution is it measuring?
So it's like the ground truth basically defines a set of chunks, and then there are occurrence probabilities. For both models, you can use this model to generate representations, which you can use the set of ground truths to parse. And then you can sort of using this way to evaluate the learning, like the representation it is learning. It's a bit convoluted with how the KL divergence is being measured. So it's a bit like you use like HCM and RNN to train on the same sequence, and then you use both model to generate like an imagined sequence, like a very long imagined sequence, and then you use this imagined sequence to evaluate the probabilities of each ground truth unit occurring, and compare that with the ground truth probabilities for these units. So that's because you want to keep the distribution on the same support set. Yeah, so that is one evaluation we did.
Okay, basically, the lower the KL divergence, the closer it is to the ground truth sequence, right?
Yes.
That's what the main thing that we need to know, right?
Mm-hmm.
So actually, it learned quite fast. Like D equals to 3 within like, I think 100. Like, what would you call an adequate learning? Like, what level of this KL divergence is considered good?
I think generally convergence is good. And yeah, I think it's like you mean, I mean, the closer to 0, the better.
Yeah, but like how many samples will you take to learn it? Like, based on like your opinion, like, because over here the training length means the number of like, I guess the number of samples you take, right, to learn the ground truth.
The training length is the length of sequence. Yes, like So it's like, for example, when you're
Oh,
here,
okay. The longer the sequence,
yeah.
Understand.
Sorry, just to clarify. So I'm saying like, the RNN doesn't like iterate on the same sequence multiple times, because then typically if you use gradient descent, you need to that, right? Just to clarify.
Yeah, it doesn't. So it's just like one part of the sequence for RNN as well. So here the plot is more about like learning efficiency, like more pronounced data efficiency, like the kind of how much you can learn given the same training length, like given the same size of training sequence.
But in that case, I think the learning rate also matters, right? Does it affect the how fast the red line decays?
Yeah, that can be the case. But here, I think we just use like the preset learning rate for RNN. Yeah, I haven't done like very extensive experiment on the learning rate.
I see. And one more point is, when your sequence becomes longer, does RNN show any like sub performance? Because I think it should suffer from like gradient vanishing things, right? That's what I know from RNN. When the sequence becomes long, its performance will degrade, right?
Yeah, I haven't observed it. Maybe I haven't trained it on like a sequence that long. But yeah, so I haven't observed it so far.
Okay, I see.
Yep. Yeah, I think like the most criticism I receive from this plot is that people usually like you shouldn't compare RNN with respect to like training efficiency, because RNN are meant to train on the same sequence over and over and over again. So yeah, so but I think like in terms of learning efficiency, there is a big difference.
Yeah, basically.
I agree.
Yeah.
Because, sorry, let me just finish.
Yeah, please
Because
go ahead.
for your model, right? There's no need to iterate on the same sequence over and over again, right? There's no use. Yeah. So I think that's just high learning efficiency or high sample complexity.
Yeah. Yeah, so it's not so easy or straightforward to compare to like other models, and this is like one of the things that we try to come up with.
You can just argue that it's just basically you train for the same iteration, but then your model has better learning efficiency, right?
Yeah, that's basically the idea. So one iteration and the learning efficiency.
Anyway, I just wanted to say like deep learning is not very well known for training efficiency. It takes very long to learn. Yeah, and that's why like this kind of approaches that do some form of pre-established rules, I think will help a lot with the learning. Anyway, I just want to point out that I noticed that it converges quite well at 1000, right? For the HCM model, like about 1000, it kind of learns the distribution already. I mean, if you look at this plot and this plot. Yeah. So actually, it means that you already learn how to do the ground truth, like sort of generation, after just looking at a sequence length of about 1000. Regardless of like this D is the number of units, right?
Yeah, number of units.
Like the number of colors over here. So here is D equals to 3 because there's green, red, and white. Like D equals 8 will have like 8 different colors, right?
No,
or it's different chunks. Or it's just the chunks.
It's just different chunks.
Okay, yeah. So it means that the main thing, I'm just trying to infer something from this. So it just means that the more chunks I have in the ground truth generation, is it doesn't really affect my learning. Like I just need the same set of sequence, provided I have like the same set of base units, like D equals to 3. Basically the 3 different colors, right? Red, green, and white. As long as you have all these 3, regardless of the number of chunks in the ground truth generation, you kind of learn the same rate. I mean, sort of, right? I mean, we look at the plots.
That's a really interesting point. I haven't thought about it this way.
So could the learning be tied to the number of base units rather than the number of chunks in the model?
The number of what? Sorry.
Base units. That means like number of different colors of the squares to begin with. Could the learning of like your chunks be tied to this rather than the amount of chunks in your ground truth generative model? Yeah. That means like if you increase like more colors, like red, green, yellow, like
yeah, we've tried that as well. Intuitively, I think it wouldn't matter as much either because you are because the frequency and transition updates also sort of goes with the sequence. I'm not 100% sure, but I feel like the number of units also doesn't matter that much.
Oh, actually, I think the number of units matter a lot, in my opinion, because that determines the number of possible chunks there can be. So if there are more chunks, there'll be more chance of you like classifying wrongly. Yeah, I mean, 3 colors, you only can have like, I don't know, 3 factorial, or basically each length of the chunk, because your chunk only has red and green, right? No white. So each chunk has a possibility of 2. So like a length 3 will be 2 to the power of 3. Length 5 will be like 2 to the power of 5 possibilities.
Yeah.
But if you have like one more color, then like a length 5 will then be 3 to the power of 5 possibilities. So the chance of incorrectly classifying one chunk will be higher with increased number of like colors for the number of squares. Yeah. No, but anyway, this is something to think about because I think if we want to abstract this to like even more complicated domains where that's why I asked about base units, like where there's a lot of possible base units, can we still use this method to learn? Yeah, or to effectively compress when there's so many different possible chunks that can be formed.
I think can, because you can just like you just follow the how we do tokenize for, let's say for language class, right? You can think of the red and green box as individual characters or letters, right? Alphabets. So that's the basic, the most basic you can go, right?
Yes, that is one of the things we tried. For the sake of time, let me move on. And
yeah,
because
maybe we let you finish your presentation, then we ask the rest at the end. Yeah. Okay.
I mean, you can jump in also, and I think some of the also like one reason is some of the questions you asked is coming up later. So yeah, so one experiment we did is like with regard to this transfer question. So it's like if you have a generative like a ground truth or you have learned a representation from one particular sequence, and then now the model is taken to like a sequence generated by like this new generative model, and then this new generative model contains like overlapping parts compared to what the model has learned before, then the learning performance for the trained model is better than like a naive model that goes into this facilitative environment, I call, that does not have any representations, like shared representations. Whereas if you go into like an interfering environment, that this model needs to learn a lot of new chunks from scratch, then this model performance at the beginning of training in this novel environments is worse compared to like a naive model who goes into this environment without knowing anything.
So knowledge is a burden. If you know stuff that is not the same kind of characteristics as your environment, you actually have a lot of extra baggage that make you not perform well, right?
Yeah, like knowledge is a merit in this case, and knowledge is a burden in another case.
Maybe that's why
because
sorry, let me finish. Maybe that's why people need to die Because like if you have too much knowledge of the world in the past, you accumulate all these structures already. Suddenly the world change, we adapt very slowly. Yeah, maybe that's how evolution built us. But anyway, yeah, sorry, please go ahead.
I'm just trying to make a comment that I think it becomes worse because you don't have an inbuilt mechanism to unlearn, right? You can only learn once in the first task. You already learned that, for example, the bronze blue is a valid chunk, but in the interfering environment, it's no longer true. But you don't have a mechanism to unlearn that knowledge, right?
Yeah.
Yeah, but I would like to say, even if you unlearn this knowledge, I still think the naive would win the unlearning process because it takes time and effort to learn a new set of representations. Yeah, but definitely the adaptability part needs to be encoded more by like changing the chunks if the chunks don't occur anymore.
Yeah, something like you need to look at different level. If a higher hierarchy level chunks doesn't work, then you need to like go back to a lower level iteratively until you validate, okay, it works, then you go from there again to start building up your chunk.
Yeah, so that's this experiment, and then I thought it would be interesting to show. I mean, it's like a very simple toy example, but it can be related to like some of the human behaviors we observe in real world. It's like when you transfer languages, it's easier to learn Japanese from knowing Mandarin compared to learning Japanese from knowing German. And then it's like, are there like languages that that it's better to know nothing compared to knowing something? Yeah. So, and yeah, this slide, I think it's more succinct. So basically in this experiment, we compared like the chunks learned by HCM to human chunk learning. Yeah, there is like actually a set of sequence learning experiments behind this comparison. So basically we ask people to do sequence learning experiments. You show them a color on the screen and then need to press the color, and then based on, it's a bit like Guitar Hero, or if you have played it, so it's like, oh, the colors keep hitting at you and then you need to respond to, like, if it is green, then you press green, if it's blue, you press blue, and if it is like pink, you press pink, and so on and so forth. So we can measure their reaction time, and then based on their reaction time, infer what is the chunks that they have learned. And then based on the chunks they have learned, we can measure like how they improve during a training session. So that is the chunk increase rate, which is like the average chunk size humans use to parse the sequence. So we compared basically that with the same recurrent neural network, and then the hierarchical chunking model, and showed that HCM learns chunks in like a similar rates as compared to human when the given the same training sequence. And then here is like we regressed the simulated reaction time based on the probability from both models to human reaction time, and then showed that HCM has like a higher standardized regression coefficient compared to recurrent neural network. So one thing we did is as John asked, or Zoe asked, so can you sort of explain this principle to higher dimensional domains? Basically, we try to explain the same principle to generalized chunk learning in visual temporal domains. And in visual temporal domains, the chunks are no longer this like one-dimensional sequential units, but you can sort of imagine them as like three-dimensional cubes. So what does these cubes represent? So it's like if you see like this X and Y, or like this plane is like one dimension of pixel observation, then this dimension, this time dimension is like, okay, like what are the pixels you observed in each temporal frame. So the chunks basically becomes these like three-dimensional objects, and then you use like similar grouping principle, like when like this object occurs like next to another object, either in space or time, then you group them together as a unit. So the marginals becomes these like weirdo cubes that are spanning in like visual space and time, and the transition. Oops, and the transitions are also like the transitions like chunks that are proximal in space and time. So we can use this principle to learn partial relationships in a visual hierarchical model. I will explain this. So this is one experiment we use to see what like does this kind of learning principle resembles like partial relationships. So this visual hierarchical model is also a generative model. So you use samples from this model to generate the sequence. And what it has is like you have like these elementary units. My inspiration comes from like Chinese characters, that you have like some basic strokes, and then these basic strokes can combine into like more complex strokes, and then it's like these complex one can combine into like even more complex one. And the observation sequence you feed to the generalized HCM is you sample like these images independently from the generative model. So you see like this thing as like one image first, and then this thing the next one, and then this thing the next one. There's no temporal correlation, but there are strong space correlations. And we use this sequence to train the hierarchical chunking model. And at first, it always learns like these pixel-wise representations, as it is like the minimal granularity it can use to represent what it sees. But gradually, when it observes that, for example, the three pixels here always occurs right next to each other, then it arrives at like these intermediate representation that some granular perceptual units are combined together into these intermediate level representations. And then based on the representations learned so far, it further combines the pre-existing chunks into even more complex chunks that resembles like more to a part of the underlying generative model. So this is an experiment we do to test if HCM can learn chunks that resembles spatial correlations. Another experiment we did is to take it to visual temporal sequences. That is, sequences that not only exerts a spatial correlation, but also correlation in time, just like real world perceptual sequences. So term this as visual temporal chunking. And basically, we have this GIF sequence of like a squid swimming in the sea. It's a bit like, I don't know, like one of the things that we observe every day. Not really, but yeah, you know what I mean, like somewhat realistic spatial temporal sequences. And then if you expand this GIF in like every temporal frame, then it is like every temporal frame, then you see like slightly different squid, but then there are strong temporal correlations, and also spatial correlations. So so basically we showed HCM like the same sequence of images again and again and again for like, I don't know, like 1,000 times maybe. And at at the beginning, it learns like these simple like things that that sort of like resembles like body parts. And then by combining pre-existing chunks, it can learn this kind of like spatial temporal objects almost. And if you have noticed that it's like this squid is separated from the backgrounds, and as the backgrounds, like for example, a rising bubble is grouped together as a chunk, as separated from like the jumping squid. So I thought that part is quite interesting because it's like this kind of object identity can be learned from this simple principle. We also have trained HCM on language data sets. In this case, it is so basically we make HCM read Hunger Games, and and what you see is it's a bit like the results is like similar to in like this type of taste. So like at first it learns like these frequent part words, such as like these prepositions and pronouns that occurs quite frequently in text. And then gradually it builds up these intermediate chunks that contains subunits such as District 12 that occurs quite often in Hunger Games. And then if you train it longer, I think by longer, like the I think even the complex chunks is it's like 3/4 into the book. And then it's well arrived at the representations as the capital, our district, to the baker, like these kind of phrases. And one final example that I will show you before we go into our discussion stage is so I've been always interested in how the brain works, or it's not like I'm not working on it, but I'm interested. So one thing we have tried to use this algorithm for is to learn hierarchies of brain activation from our brain recordings, because it is related to this theory in neuroscience that brain, like there is like a network of activating functional units that exist in our brain. And another reason is if we are very good at grouping things together as a unit, then is this process also implied in our neural activities. So it's like, given this couple of reasons, so we have tried to use a set of fMRI data. If you don't know about fMRI, basically it is a set of recordings in the brain that contains, like, you can have like labeled regions, and then in this case subjects are watching a movie, then I get to know about like what are the regions in the brain, and what is like the time series of activation. So it's essentially like a high dimensional sequence. It's a 4 dimension. 3 dimension is like 3D in the brain, and then 4 dimension, the 4th dimension is time. So HCM can be used to actually discover patterns of functional activity in the brain, which is something that is quite surprising to us. So in this movie, I told you they are watching like an animation, and I'm showing you the time axis from 0 to 168. This is in the unit of repetition time, but each repetition, like each unit is 2 seconds. And at time like 66, there is this thing happening that this cloud is greeting the crane. Or if you have watched this movie, it's actually quite fun. So the original study was looking at whether there are like the theory of mind-brain circuits in relation to this movie. But what we can do is when this greetings and hug happens, we can look at what are the chunks, is that like chunks of brain regions that activate like together after this thing onsets. And then it's like HCM learns these chunks, but how do we know like if these chunks are relevant, right? So yeah, another example is social interaction. When there is a social interaction, we also see like other chunks lighting up. What I want to say here is, so for example, the left to right dorsolateral prefrontal cortex, later we looked it up and it corresponds to theory of mind circuits, when like that is correlated with when subjects are inferring or like looking at a social interaction scene. And then this like dorsal anterior cingulate cortex and Broca activates when subjects are having a conversation. So basically we found some neural evidences on the meaning of these chunks that HCM discovered. So another interesting thing that HCM can tell you is this like nested hierarchical structure that underlies co-activation for brain regions in this data set. And so basically using the set of chunks, you can draw this nested hierarchical graph. And for this example, we looked it up, and it actually corresponds to like a network of activities, and this network would mean that these brain regions, they coordinately activate together, but then also like this sub-modular units that is embedded in this bigger units also coordinately activate, but in some other tasks. So so in summary, we can sort of use this method to discover nested network of brain activation patterns. So yeah, I was quite excited about that, and I hope to, if possible, like if this algorithm can be used for helping neuroscientists discover what is the network of brain activities, so that we can better understand ourselves. So that brings me to the summary, or if you want to have a take-home message. So we proposed HCM, this hierarchical chunking model that is like a cognitive inspired algorithm based on inspired from chunking, and it learns nested hierarchy of chunks. And the good thing about this nested hierarchy is that this algorithm is especially suitable when the underlying observational sequence contains nested hierarchies. And then my hypothesis is like actually most perceptual sequences contains such nested hierarchies, which can render this chunking strategy very useful for cognition and behavior. So a good thing about this algorithm is that it learns representation that are interpretable. So you know, like what are the chunks, like what do they look like, and you can also reuse them when you encounter a new task. And in terms of applications, it can be used to discover patterns in spatial temporal sequence data, and also resting states fMRI recordings. Yeah, so that summarizes my presentation, and we can move on to discussion stage, or if you, I think I went through some of the slides quite fast, so if you have questions, please ask.
Yeah, I'll reserve my questions near the end. You have anything else to ask first? Because I think mine will take a while, my question to answer it.
So for the temporal plus spatial experiment, I would imagine that the chunk to learn should also reflect the temporal relation, right? The octopus one.
Yeah.
But then I only see the chunks like becomes like the body parts of the octopus, like this. I didn't see the temporal part.
Yeah, so for this example, it's like I take the spatial parts, but this one is like a temporal sequence, and it's like, yeah, when
Oh no, like oh, so that's one chunk, right?
Yeah.
The four frames is one chunk. Oh, I get it. Yeah, I
Yeah.
get it. Can I go back to the next slide just now where you coming back to the next one, sorry.
Language datasets or
Oh no, the one with pattern, the spatial one, sorry, the spatial one.
this one?
Oh yeah, correct. So the sequence, I think you mentioned that there's no temporal relation, but it's spatial. So what was the spatial relation here?
Yeah, the spatial relation is described in this like hierarchical model. So it's like simple units combined into like
Oh no. The sequence. For example, how is the second frame related to the first three and the third one related to the second and so on and so forth?
there are so it's like first, second, third. They're independent.
So they just randomly sampled from.
Yeah, random samples.
I see. So it's not like they progressively become more complex, no, right?
No, they don't
Okay.
progressively become more complex.
All right.
Yeah, I think maybe progressively becoming more compressed can be better for learning, although I haven't tried it. But here is like random samples from the generative model.
I see.
Is that you can have maybe a curriculum that like HCM learns simple things first, so you make sure the simple things are correct. Then you progress to like a middle school curriculum. Then maybe it's better for learning. I haven't tested it, but it's quite straightforward.
Yeah.
Oh yeah, anyway, on this slide, I have something to point out. I actually like this way of building up the visual hierarchy. So just want to highlight is that unlike a conventional like CNN, like convolutional neural network, you don't actually need to follow up from this layer to the next layer. Because I mean, there's also links from like any chunk that you have formed before can be used to form your next chunk. So you like this chunk over here is from the ground layer 1 and layer 2, you combine together to form this one, right? This is correct, right?
Yeah.
So there's actually not really, the hierarchy is not really very strict, because in terms of your model, you're actually using your pre-established chunks to see which can match together to form a new chunk, like chunk A and chunk B, which one has the highest like statistical probability to form the next one, right?
Yes.
And in the visual case, the sequence doesn't matter. I mean, it can be A first or B first. Both ways would actually work, because like there's no like temporal element to it.
Yeah.
So actually, coming to the point on this sequence here, I noticed that in order for HCM to work, you kind of need the base units in your sequence. Like you need your this one. Basically, the units at this ground level here, you need the ground units to be in your sequence so that you can start chunking them first, right? So what if, let's say, the sequence that you see is already the complex image, like the world itself, like you see your tree, your computer, everything in the same frame. Then can the chunking still occur? It's something like the octopus, actually. Yeah.
Yeah, it can. It's like it's like you can also, because the representation always starts from the minimal granularity. So it's like the representation always starts with simple pixels. And then it's like, in case it is already like quite a complex sequence, then it's like this process, this building up from simple to complex process will occur regardless of like the complexity of the sequence.
Yeah, I understand. So if like, let's say the input is only this tree, what the model would probably predict is that it will predict like a straight line here because all three of them have the straight line. The model will also predict probably the cross, something like that, because all like three images, two of them have this. So you can still get your like ground units from the observation, just that the ground units won't be, it probably won't be like this because there's no, it will be more like this kind. So
yes, so it will always start with something like this.
oh, it was
and
still
then
the single unit.
It's always starts with like the simplest one, and then at one point it will probably build up into this representation.
Oh, okay. So you will still have this simple, intermediate, complex, regardless of like how your input sequence is.
Yes.
Oh,
And
that's actually very interesting. Yeah.
And the difference is if you just feed sequences from like these three sets, then maybe like it's like the dynamics of progression will be different. The like given the same, like if you're feeding the same length of the sequence, and then you look at the representation at the end of like the 1000th frame, then comparing this generative model versus like the entire generative model, like the representation will be different, but you always start with pixel and then build up to more complex. So it's like the dynamics of a representation graph progression can depend on the generative model. But regardless of any kind of generative model, the graph always progresses from minimal to more convoluted ones.
It's quite cool. How do you decide the number of chunks to accept for each layer, like simple, intermediate, complex? Like how do you decide what's the limit of chunks to get?
Yeah, so maybe the terminology is a bit confusing. So so by simple, so there is not really like a clear boundary between simple, intermediate, and complex.
Okay, basically you have no
rather,
limit for simple, intermediate, complex. You just have an upper limit for the number of chunks.
I also don't have upper limit for the level of chunks, but at one point the number of chunks will stop increasing.
When there's no more like statistical correlation anymore, then it will stop.
Yeah.
Also, it's a self-terminating algorithm. Actually, I find this very cool because, you know, this whole part-hole thing, you know, Geoffrey Hinton has been trying to do this in his, like, there's this network called
we're trying to decipher the part-hole thing also recently.
Right. But I think his approach using backpropagation hasn't been successful because I think in order to learn all this simple, intermediate, complex, you want to learn it through like backprop. You may not have such a clean identity as what you have over here, which is the like these dots over here. Because I've tried before, I visualized like a CNN like network. The basic level filter, you might think is actually very simple, like lines and stuff. Actually, it can be a lot of noise. Yeah. So this actually has the elegance that the part hole is really a part hole because that is built into the structure of the algorithm. You actually combine them together in order to form larger and larger chunks. So I like this. And I also like to link this to you know, Yann LeCun's idea of unsupervised or self-supervised learning, where like babies, they observe the world of a long time, then they form some representation or they learn something just through observation, and then they can use this to do the task later on. So it seems that this can actually account for self-supervised learning as well. You observe like a certain amount of chunks, a certain amount of sequence, you build some base level chunks, and then later you can just use these chunks to do like some form of like characterization. So you may not know what these chunks mean, but at least you know like how to represent your data in the most like statistically efficient way, because like you see this data appear a lot of times in the like form of a plus, so you represent it in the form of a plus, and then you can use that to do your your semantic meaning. You can do your semantic meaning later. So I think earlier on I asked about semantic meaning versus like this chunking. I kind of figured out an answer already. The chunking might actually form the base units, right, for meaning. So you actually can, like, you observe, then you chunk, then you can associate meaning to the chunk.
Yeah, I'm glad. Yeah, I think that's also like related to one thing that I'm currently investigating. How does concept arise? Yeah, I'm really glad. So it came to you as well.
Yeah, no, because in word embeddings, how they do it currently is this thing called, I'm not sure if you're familiar with it, it's called byte pair encoding, where they actually use also statistical correlations to group the most commonly occurring pairs. But they probably stop at pairs, the byte pairs. But if you could do this kind of hierarchical coding, you can actually get more meaningful like identities. Yeah, because for what? Sorry.
Just to clarify, how is this byte pair encoding different from next token prediction?
Oh no, it's just a way of representing word embeddings. So byte pair encoding will form like the tokens. Like they will actually chunk. It's also chunking, but it's at the level of like byte. I don't think they chunk more than 2. I could be wrong. I have to check the algorithm again. But the byte pair encoding is something like chunking, where they chunk together statistically significant words or subwords or tokens. Let's call them tokens. They chunk together tokens, and then that will form the like base level tokens, which we then use to perform like the transformer on. Like each token will have its own hidden embedding space. Yeah. So it is quite similar. So you byte pair encoding, you get your tokens, and then after that, you get your.
And then the tokens are passed on to like transformers.
And then you get your embedding space. Yeah, your word vectors from the basically your token vectors.
Yeah. Which brings me to the point I want to address here is so I have been thinking like for a very long time if neural networks are representing chunks, because it's like if they are like they can learn any type of functions, so chunking can be like one functions that they are learning. So so there are two questions. One is the manifestation of chunks also can be found in intermediate layer activations of transformers, recurrent neural networks, and CNNs. So that is one question, and my hypothesis is it should be there, or it's like you should be able to find manifestation of chunks from the hidden units. But although I've been stuck on how to find them, and then the second question is if combining chunks can be a faster way of combining previously learned representations, can you exploit this principle to speed up neural network training?
Yeah, I think one obvious way I can think of to speed up neural network training is that your chunks can form the fixed representation already. Like for example, CNNs, you have filters, right? So actually recently I've been also trying to work on this thing called fixed filters. Okay, I'll give away my idea right now, but it's okay. So basically, like rather than learn like all these pixel embeddings in the filter, which takes very long and sometimes it's a weird embedding, why not start with like human established priors, like a straight line? Why not just fix these filters into some like layer and then see whether it activates or not? So I guess
that just goes back to the old era of doing computer vision, right?
Yeah. So I haven't finished yet. So I just thought of an idea with your chunking. Can you learn the chunks already, and then use these chunks that you learn as the fixed fielders. So in some sense, it speeds up the convergence of deep learning because you don't have to learn the representation anymore. The representation is given based on your observation. So like this chunking part could be the self-supervised learning that LeCun is talking about. Like you learn through observation of like the world. So you form chunks already through your observation. And then you use these chunks to do your decision making and processing later on. Yeah. Does that sound plausible? Like, so
that sounds really hard to do for this algorithm, because I think like one good thing from deep learning is you can sort of process very high dimensional data, and one challenge for this model is scaling up. So it can operate on like semi high dimension, but not like the kind of pixel space that you see in ImageNet, for example.
Yeah, no, that's also the problem with the system we are using right now. Our images so far are high dimensional, like RGB pixels with like different pixels, like for each image. Like an image can be like 256 by 256 pixels. I think that is too much information. So like in the visual system, actually we only have like rods and cones that pick up differences in light between the surrounding regions. Yeah, so perhaps our input space is just too much. I was thinking of also using something like a JPEG encoding. So JPEG is basically like brightness and then yellow, blue or something like that. Yeah, yeah.
I have suggestions on this part with regard to the kind of basic elementary units you use to process the image, because I worked with visual models before, and look up steerable pyramids, because it's more like a set of bank of Gabors that back in the days vision scientists, I mean, they still do use it to sort of represent the elementary units in the visual perception. Bank of Gabors, or
How do you spell that?
Pyramid, or like visual pyramid. I can send it to you.
I only know the FPN network, the focal pyramidal network, which is like you can see an image at different scales, which I like it a lot. Yeah, because it both the visual
it's not that. I think it's yeah.
What's the problem with pooling? Why can't just use pooling?
Or to reduce complexity, is it?
Yes, that's how CNN does it, right?
It's possible to use pooling. You will just lose some information. As long as you don't pool too much, you should be fine.
Yeah, so because I think your problem is you are thinking there are too much pixel, right, which is redundant. Then we just do pooling.
Yeah. I think there is a way to reduce the complexity of the input space so that we can do this chunking algorithm. Because based on what I see so far, the chunking algorithm can chunk like even with a very complex input space, because all you need to do is to reduce the number of base units. Like so far, this model can work because there's only two colors, right? Like brown and blue. But
yeah,
let's say there are 16 different colors, then the number of chunks will increase exponentially, right?
yes.
So we just need a coarse grain solution whereby instead of like representing the RGB as 255, maybe you represent it like as 8 different levels. Yeah, then maybe this chunking can be feasible. So it's something like compression, where you compress like related spaces, related inputs together, like through some, I mean, it could even be an autoencoder hidden representation, you know, or it could just be rule-based compression like max pooling, or pool by like the different pixel intensities. Yeah.
I haven't tried autoencoder, but that's maybe, yeah, I will look into it.
Yeah, I think if you can maybe pull this thing, I don't know whether it makes sense, but let's say if you manage to do your chunking at a reduced dimension, so the reduced dimension can be autoencoder or it could be rule-based. If you can do it in a reduced dimension, then you can chunk in your like sort of latent space, in this reduced dimension space or latent space, and then you can then map it back again to the input if you need to. Yeah.
Mm.
Yeah, because I feel like this chunking itself can be the way to generate the representations already in like most like CNN networks or like those hierarchical networks. In fact, it even incorporates ResNet. You see, look at this. ResNet is skip connections, right? This is a skip connection. The reason why we use like skip connections is because the traditional layer-based method actually is an artificial construct. You know, in the brain, the neurons don't follow layers. They actually all do by clusters. So that is really an artificial construct. And chunking doesn't have any layers at all, actually. It's all based on like ground units and then you build up. Yeah, so I think there's potential to use this to do like abstract representation. But the only catch I can see is that your input space here must be simple enough. If not, your chunking algorithm can find a lot of like spurious chunks. Yeah. So yeah, I think that's more or less. Yeah, I really like this idea because you know I've been doing my memory mechanism as well, the fast and slow one, and now I'm stuck at the problem of trying to abstract the memory space so that you can actually learn to associate what you have learned before to more environments. And I have this feeling that like you have to artificially make it like simpler. You need to store the memory in a very simple space, and maybe you know, if you could sort of chunk whatever you see before, your chunk could be a way to like represent your memory in a simpler space. Also, there's two different ideas here. One idea is to use like compression to make your chunking easier. The second idea is maybe you can use your chunking as a way to compress, or as a way to represent things in a simpler way. Then you can reuse the chunks. Yeah, I'm still thinking about it. Yeah, we can discuss more about this. But I think there's a lot of relation between this chunking and abstraction. Yeah.
One more question. So I think the simplest, you have to define the most basic granularity to your model, right? For example, in this case, you have to tell your model your simplest structure is the pixel, right?
No.
Then how does the model know where to start from?
It starts from nothing.
Oh no, but sure, I think what Zhe meant is that you need to tell it like the basic unit is like this one brick. Yeah, so that it knows that this is the first chunk it should create.
Not really.
Yeah.
So the starting representation is empty, and then it's so it's like it uses the representation to explain the observation, and then if no like when you start with it, then there is no representation, so you don't have any observation, and then you start to accept, okay, the minimal pixels, or like then you start to accept the minimal units.
But how do you construct the even one pixel if you just start from an empty set? You can't compose your empty set to create something out of nothing, right?
You can.
Because in the sorry, just so in the very beginning, you explain to us you have the basic unit which is like red and blue, I think. Then you compose.
No, you don't have.
I don't have to.
No, I think it's also, the question is also related to how this sequence, like how the sequence is represented. So so here it's like an image is not a 2D array, but rather the image is encoded as in this location X and Y, I see like this value. So it's like a pixel is like a tuple. And then a sequence is like, here there are 3 observations, so it's like 3 tuples being observed, and then here it can be like at position 5, 0, I observed a 1, and at position 5, 1, I observed a 1 as well, and another position like 4, 0, I observed another 1. So so basically so in this way your sequence is not a 2D array, but a set of tuples that represents observations, the observation location and value in each temporal point. And so to parse such sequences, you don't need to assume there are the minimal pixels, because if you have nothing in your bag of chunks to explain the sequence, then you accept the minimal tuples. Does it make sense?
So the minimum tuple is not pixel.
Yeah, the minimum tuple is pixel. But for
so
example, yeah. So after looking at this image, then it's like as a model, as a naive model, after looking at this image, then it learns 3 pixels. And then after looking at this image, it learns like 5 additional pixels.
Then Choming's previous question should be, his understanding is correct. You don't start from single pixel, right? You start from the largest possible pattern you can have.
No, you start with. No, you start with nothing. So it's like after the first image, then you arrive at 3 pixels, and then after the second image, you arrived at 5 additional pixels. But it's not like the entire pattern. And they are like these scattered pixels.
Yeah, I think to add on to Zeri, I know you have to leave, but this is the last point. So in order to get these simple representations, we kind of need to know the size of the simplest pixel, right? So that at least must be provided to the model, right? How big is the smallest pixel?
Yeah, that's for sure, yes.
Yeah, I think that was what Zeri was asking. So that means the minimum chunk will always be provided to the model. You can't really like infer the minimal chunk from your data. You need to tell the data like, then you tell the model, okay, my minimum chunk is like this pixel, this size of a pixel, or the minimum chunk is 1 letter, like for the word chunking model.
Yeah,
right?
that is like integrated into the sequence representation.
Correct. So that is provided as a given already to the model. Then we use that to start doing the chunks, which will then tell us where are the most frequently occurring pixels at, which group of pixels are most frequently occurring, and all the way until the most complex representation.
Yeah.
Like, yeah, that's how the chunking works. Right? That's correct, right? Yeah.
Yeah.
Okay. Anyway, I think do you have to go already, Shuchen?
Well, not really, because my supervisor canceled my meeting.
Oh, okay, great. Then we can
I
talk
actually
more.
don't have the time constraint anymore.
Oh, that's great. That's great. Yeah. Yeah. So we can continue like discussing a bit more, maybe like 5-10 minutes. Then we wrap up.
Sounds good.
Yeah. Do the rest have anything else to ask?
Yes, I also have one additional comment. So I feel like this algorithm has like a more general inductive bias compared to the current state of deep learning model. So the hierarchical is like the most, so far I can see, the most fundamental structure of the data. It doesn't matter whether it's language or it's image or whatever. You always have this hierarchy. So I think basically I think exploit this even more fundamental structure is a very good thing. But I also realized I feel like there might be some limitations, because this hierarchical way of learning the chunks, right? It explains the patterns or the representation of an individual unit or individual chunk, but it doesn't give a good description of how different chunks are related to each other. So for example, like in attention, you can explain different words, how it's related to another word. Despite the fact it belongs to different structure or different phrase, you still can explain the strengths of the connection. But yeah, I didn't see that characteristic here.
So it's like there is like a context dependency. For example, if you are, it's like depending on the context, you may pay attention to some particular relations to the between chunks compared to others, even if it's the same set of chunks.
So do you have something like that here in built in here?
No, that is that is indeed a limitation, and I think which is the reason I think this algorithm by itself is quite limited, but should be like it's I always want to combine it with like some of the pre-existing methods to have this like context dependency. Yes, and so far this thing just addresses like chunking.
I see. So you can combine things like attention plus chunking. Maybe.
Yeah, right. If someone gives me like 2 months out of the blue, I will work on it. It's like currently I'm just like caught up on like this whole bunch of things, and then I don't have time to work on it. But
I see.
Yeah, don't worry. This one I think can be done if we have some like actually we can all help to like do certain parts of this if you're interested to follow up this, because I do think sorry, say again.
Definitely. Yes, please. If you're interested, just take this model, and I can help. It's like this one. This is one of the things that I need to go to work on and to do experiments, collect data, and then at the end of the day, it's like, okay, what about neural network? How do we combine it? I don't have the time, but.
Yeah, no, this one thing I feel like for PhD, it can be quite difficult, because if you need to do like your base set of experiments, sometimes you just don't have time to think about like how to extend this other, because there's so many possibilities. You have to focus on one. Yeah. So actually for me personally, I quite like being at the level of ideas and having people to do the ideas. So actually I'm more at the level of a PI than a PhD student. But it's okay. Yeah, I still think simple experiments are the way to go to like test out the ideas. So you probably don't need 2 months. If you want to link this with attention, maybe, so you want to say like your idea of how to combine with attention, then I can help to see like how we might go about doing it.
I have not thought about that in detail. I just have this idea just after I listened to the presentation, then I just started thinking why I didn't see this like connection. Then I just draw some link to, or maybe we can, like as what Shuchen just mentioned, right? If we can combine it, then maybe it works. So I haven't had time to think about it yet. I can give it some time to think about it.
Yeah, I mean the most easiest way to link this to attention is to use this as the base level units for the tokens. Like your chunks will be the base level tokens. Yeah, then you apply the whatever attention transformer method on your tokens. So like, the byte pair encoding I was talking about earlier.
Yeah, but it's very similar.
Yeah, so replace this with like the chunking method, and you can
so something I was thinking is throughout the talk, like because currently I think someone also asked in the chat, right? The current language model does not make use of the hierarchical chunking. So it just have one level of tokenization, which is effectively the chunk. So but this method, like just now we see, like give rise to different level of chunks. So maybe that is useful to to encode different level of hierarchical structures. But I think in the language experiment, the chunks stop at around two word short phrase, right? If I remember correctly. Yeah, so basically I think so that's why I think by this chunking mechanism alone, they kind of fall short to really capture the language, the patterns in the language. But then it does have this because we already have different level of chunks, we know like what's the effective way to combine them. Then maybe we can do something in how do you actually tokenize your sentence? Maybe the current way to do encoding is not the most effective. But then maybe this algorithm, from this we can learn a more effective encoding. I think it's the similar idea as what Chomei mentioned for vision, right? You want to learn the most effective basic structures. I think it's just the same for language.
Yeah, actually I just took a look at the byte pair encoding method, right? Actually it's very, very similar to this chunking. Basically they take the most frequently occurring pair and they take out that as like, they make it a super symbol, like maybe like AA will become like the word X. Yeah. Then after that, then they will look at, after replacing that as the super symbol X, you look at the whole sequence again, they take the most frequently occurring pair, and then that will be a new pair. Then you just keep adding that to the dictionary, like the base level tokens, which is actually very similar to what is done here. Like you take this out into your dictionary, then maybe you take this into the dictionary, then you just keep seeing the most frequently occurring pair. Yeah. So in some sense, byte pair encoding might already be doing what this chunking is. It's just the difference is perhaps what they do the part-whole relationship from is from one like static sequence, and then like they just merge. So the sequence is not exactly like that. The sequence will be like in individuals. If you're talking about the visual part, the sequence for byte pair encoding will be the base level units already, which is let me just read. The starting sequence of byte pair encoding will be this one. This is the starting sequence sample, from the sample one, and then they just keep drawing out the patterns from it. But what this chunking can do is that it can already get the all the nested relationships from all this kind of data, like more complex data, which I don't know whether there's a difference, because I
think there is, right? Because in the way you just described, you take the most frequently occurring pair, you take them, then you don't care about them anymore. So you only have the most basic level. But here we actually can reuse that as another unit, then can compare the frequency again.
Oh, no, byte pair encoding also compares the frequency of the merge symbol. That symbol will then be compared with the whole sequence again to see whether there's additional most frequently occurring pair will then become the next super symbol. So maybe let me just explain here. Like, for example, you have this sequence here. Yeah. So I have this sequence. So byte pair encoding will see, oh, A occurs quite frequently. So I will then do this. Yeah. Then over here, you can see that there's no more symbol left. So this is the end of the encoding. Yeah, you encode the AA over here, and there's no next level of symbol. But if let's say I have another B over here, right? Yeah, if there's another B over here, what I can do is I can then have the XB combined to a new symbol Y. Yeah, so other than just only having the base level units like A, B, C, D, E, my dictionary will then be like that. My dictionary will be then A, B, C, D, E, X, Y. Yeah. That is a very rough gist of how byte pair encoding works.
But it sounds very similar now.
Yeah, no, maybe Shuchen can say. I'm very sure there's a difference between this model and this.
I mean, it is really similar. It's just I think at one point, also people started to point this out to me, and then I looked it up, and then but it's I think from the motivation to use byte pair encoding, it's more pragmatic based. It's at one point Google started to use it, and it helps transformers to train quite well. And I think chunking is really similar to it, but here I think the project is more about why is it so useful. So I think I don't mind the resemblance, but what I'm really curious about is if it's if you can use this type of chunking for multiple layers of transformers. It's to make the tokenization process more efficient. Is it going to? So it's in the input layer, if you do in the pre-processing, if you do byte pair encoding, then it's improves training. If after you have learned about the first layer, and then you do you apply this chunking to tokenizers in higher layers of hidden units, does it also help with training? Yeah, I think it's.
Yeah, I think the byte pair encoding is only meant to get the tokens. So these tokens can be used at it's probably used only in the first layer, because
it's just used in the first layer.
Convert it to embeddings, then the rest of the layers are just embeddings already. Yeah. So Well, I don't know whether you can do byte pair encoding or chunking for hidden layers because you see, chunking only works when the number of symbols are small, like the number of initial units are small. Like in this case, like you want to talk about the alphabet, there's only 26 alphabets, like A to Z. Yeah, if you want to use it for a multi-dimensional space, then the number of starting symbols will be exponentially many, which I think chunking will have difficulty doing. I don't know.
But but it's like amongst attention layers, the output is like a fixed dimension. And then there are some, like monster transformer layers. There will be, usually there is like a fully connected layer, and then there will be like a fixed amount of tokenizers. What I'm wondering is, like, for example, if there are hidden units that, like, there is this like several hidden units are conveying the same information, or several hidden units are like they keep having like a similar pattern of activation, then chunking them together or identifying these several hidden units activation as one thing can help with like the subsequent transformer layer. I don't know, just thought.
So yeah,
I feel there's still some difference. Like the principle of doing this byte dense encoding, like you want at least there's a twice occurrence of the same pattern, then you group them together, right?
Yeah.
they only do by pairs of they do by pairs of letters or pairs of
I
symbols.
think it's possible to come up with some example where you arrive at different chunks with chunking and this, because they are doing the grouping differently, right? They follow different principles. Just like just now, initially I thought it's just minimizing the entropy, but turns out it's not. So I think we also can come up with some examples, differentiate this from chunking, because they follow different principles.
Yes. Yeah, I think byte pair encoding is minimizing some complexity measures.
Oh no,
It's
actually
more
byte pair encoding is just a set of like rules also. Yeah, it could be very similar to your chunking also. Yeah,
It's similar, but it can come up with contact example, I think.
I guess so. No, but the idea it isn't about how different it is, I guess. Yeah, I mean, it could be similar in some sense, but the idea of getting the most statistically significant one and merging them into a larger chunk, I think that's the key idea.
Yes, but remember just now we discussed like minimizing entropy doesn't always correspond to the structure in reality.
Yeah, we are not
So it can-
minimizing entropy here, you see. Right, byte pair encoding.
No, I'm just drawing some analogy.
Yeah, in fact, actually, for most digital processing systems, you can't directly minimize entropy. It has to be some fixed set of rules, and then you try your best to get closer and closer to the Shannon entropy. Yeah, which is basically like what has driven information theory for the last 20, 30 years. And now we have gotten quite close already. Yeah, but the idea is entropy is not exactly like in your system itself. You have to engineer a system to try to reach that entropy. So in this case, the byte pair encoding is also an engineered system where they just take the statistically most significant pair and then just subsume it under one bigger pair. Yeah.
Sorry, I think I was cut off just now. I think the most straightforward way is just to run the same experiment on the sequence, right? Comparing this with the chunking to see which one performs better. The very first experiment you showed us. Yeah, you can just run. Just now you compare RNN with your chunking. Now you compare this with this encoding with your chunking. See which one works better.
Yeah, I think that's possible.
Yeah. Anyway, on a separate note, I like to propose a modification to the algorithm. Yeah, maybe we want to go back to the probability table. You know, the one that I said that that one might scale up exponentially. That one. Yeah. But you just just now we discussed and then you say it doesn't.
Oh
Yeah.
no, yeah, the demo again. Oh, sorry, I will just
Yeah.
look here.
Yeah, okay. Let's just look at this slide. Yeah. So
Mhm.
I'm just thinking, because if you want to do something like this, whenever you do this transition probabilities, right? You kind of
Mhm.
need to evaluate the whole sequence again whenever you get a new chunk, right?
Mhm.
Correct. So you need to like do the computation again on the entire sequence. So byte pair encoding also does the same thing. You need to compare to the entire sequence. I'm thinking, right? Like, because I strongly believe the brain doesn't really store probabilities, but it probably will store like memories of how frequently something occurs. I'm thinking whether or not this algorithm could be adapted such that like you only compute for like the new symbol that you see. So like, for example, like this sequence over here, this sequence, probably what will happen is that you can only store a fixed like window. Yeah, because
Yeah.
you probably cannot remember all your memories, right? Can the
Yes.
algorithm be adapted such that you can only have a fixed memory window, and then you compute this transitions based on like that fixed window, like a shifting window, I think.
I see. Yeah. I think that would be like a very easy adaptation.
Yeah. Then moving on, can we even do away with the fixed window and just only look at this thing here? Because then what we would need to do is we need to have adaptive probabilities here, that once you add on, maybe not just one, maybe two of them, like two symbols, like I don't know, maybe you need to have a certain window here so you can have the chunks.
That is actually already in the algorithm.
Oh, you only
So
need
we
to
have
see
two
the next
versions.
block.
One version is like you take the entire sequence and then you use the entire sequence to learn the set of chunks. And another version is the online version. Basically, what you're suggesting is like you don't use the entire sequence, but just update the frequencies on the go.
Yeah, I like that on the go one better. Yeah.
Yeah, then you can use that one, or which one is your favorite? Yeah, but the taking the entire sequence is like more rational, but update on the go, it's like you can make mistakes, but it's online. So yeah, I did both of them, and so
Now, how's the performance like for the online one?
the performance is not bad. I mean, it learn. So for example, the demonstration I'm showing here, so these are like all from the online HCM.
Oh, do you have the online HCM model here so that like we can see it, or you don't have it in the
I
slides?
don't have it because they are so closely related to each other. But the online one, so the online one doesn't, for example, then this learning guarantee doesn't hold anymore.
Oh no, I don't care. I don't care about that. Don't care about it. Let's just talk about
Yeah.
how the online one works, because I find all these mathematical guarantees hindering us from true progress. Even to have mathematical validity, you are kind of constrained to kind of fixed kind of environments, because you cannot really do adaptive environments very well with some math proof. It's just not in the nature of math to do that. Yeah, math needs very strong assumptions, very fixed environments. Then you can do some guarantees. Yeah.
Yeah. So yeah, so for the purpose of convincing my supervisor that I want to write this paper, I need to have that part as well. Yeah, so it's like I also did this experiment on the online one and it also converges. But I don't
Maybe
have a slide
can you
for
just
the
explain like what's the difference if we do it
yes.
online? Like
So the difference is that for the rational, so it's like we're talking about the difference between the rational HCM and the online HCM. So basically, in the rational HCM, you give it a fixed length sequence, and the model, so the entire sequence is used to evaluate like the probabilities, and then based on the transitions update. The online one, it starts like the online one at every parse, or like at every parsing point of the sequence, it's like, okay, I start from here and then I parse these two together and then update this chunk, and then I parse like another, like this set together, then I update another chunk. So this process is updated on the go, and at every single update, you also update the transition transition frequency, and at every as you update both the marginal frequency, which is how often each chunk occurs, and then transition frequency, which is how often one chunk follows another. That is at every parsing step of the sequence, you you also update the set of chunks. So this entire process is renewed at every single parsing step.
Okay, let me rephrase that. All right. So basically at every step, when you generate a new chunk, you will start off with memory of 0 here. So you don't know what's the frequency, you just put it as 0, right?
Yeah.
And once you get more and more online samples, they update these numbers to be +1 or +2,
Yes.
And then after that, all these things at above that already have chunks. All these already have fixed numbers here. Yeah. So you then basically, as you progress more and more, the chunks that are already formed, like for example, you already form, let's say from this one to this one, you already formed this chunk, you will just ignore this number here so that you won't use it to find out what's the next chunk to use. So you just basically store a memory array that keeps accumulating frequencies of one chunk following another.
Yeah.
Based on your already known chunks. So if you want to insert a new chunk inside, that chunk has to start from scratch. The memory has to start from 0.
No,
Then if I create a new chunk, then what will be my numbers here? The frequency numbers.
The transition from new chunk.
Yeah, if I create a new chunk, then how do you know the numbers here?
Yes. So you can start from 0. And another choice is you can start from the estimated transition based on the sub chunks. So you can there are two choices here. So either you can start from the once you have formed this additional chunk, you can start from the transition that this chunk follows other chunk. So it's basically you copy all the entries from this chunk to other chunk to this additional chunk, because and any other things following this chunk can be following this chunk at all. As well.
Actually, yeah, it makes sense to use the prior frequencies of the smaller chunks. Yeah, so that's what you did, right? I guess for the online.
Yeah. So I have both versions, and I think currently I'm using copy the transition from this one to other ones, and then transport.
I really like the idea. So basically, if you combine this chunk to this chunk, then you can basically just use the probabilities of this chunk to the next chunk. Because you already have the probabilities over here, you can then just copy paste the probabilities into this chunk.
Yes.
Yeah, that makes sense. That makes a lot of sense. Yeah. Then you can then do this online, because the small chunks sort of store the probabilities for the larger chunks.
Yeah.
But what about then if your new chunk over here, what you then do is then you take the probabilities of whatever comes into this chunk, right? So because your larger chunk is a combination of both, you will then just take the probability of whatever transition comes into this already known chunk here, right? So then you can update this side of the table. Right? Is that roughly what you did?
Yeah, the table will augment to
okay. Yeah, I like this idea, because this means that whatever you learned already in the past few sequences, you don't need to refer to this sequence at all. But all this knowledge is stored in this transition table here. And actually, this transition table is actually very similar to my memory transition table, because you have a state, then action, next state. So actually, this transition table, you can store the number of occurrences in that memory reference, in that transition itself, which you then build up larger and larger memory. Sorry, I just pause here because I'm starting to think that this is a viable construct for my memory mechanism as well. Yeah. Very interesting, very interesting. I like it. Actually, I like it more than the rational hierarchical chunking. Yeah. So if you were to do this by constantly adding chunks and updating your like base chunks. I think this will then be the difference with byte pair encoding, because byte pair encoding is static. You only learn from like whatever you have in the base text and you keep doing it. So it's more or less like your rational chunking model. That is more or less byte pair encoding. Yeah. But if you were to do this, there's also a difference in byte pair encoding. The byte pair encoding, it starts off with the red and the green as your initial chunks already. So it already starts off with all the base units as your chunks. But yours doesn't seem to start off with like red and green, right? Right. You don't really have red green, right? For this.
Yeah, with the online version,
Yeah.
like
No,
if
but how do you get this green red without red green? I mean, you need to have these two linking here, right?
So it's like with the online version, you always go into the sequence having an empty set of representations, and then you sort of encounter this thing, and then you don't know what it is because there is nothing in your representation that resembles this item. So you just put this item into your set of chunks. And then the next one, I've never seen this before, I put it to my set of chunks. Correct. And so on.
So it means that in your list of chunks, you are missing two chunks here, right? You actually have the red and green here. So in your set of B.
Yeah,
right?
this diagram is slightly wrong.
This diagram didn't include the red and green, right? If that's the case, then your rational HCM is exactly the same as byte pair encoding. But that's not a problem. I mean, it's all right to have similar ideas. It means the idea is good because the idea works very well. Yeah. So, but I like the online one better because the online one learns over time.
Yeah, it's more. I think it's more cognitively plausible.
Yeah, because we don't store the whole sequence of whatever we observe in our entire lives or in our brains. We'll forget them. In fact, what we can do here is we then forget chunks as well as we learn online. So what happens if you can basically forget a chunk if it falls below a certain threshold?
Yes.
Yeah.
It's like at every parsing step, there is like a memory decay. So it's like all the values decay, like you basically multiply it with a decay value, like 0.996 or something like that. And then
maybe you can do an exponential decay. But what I was thinking of is maybe you can do by competition. Like, in evolution, everything is by competition. You can then do by competition.
I haven't thought about this.
Yeah, the lowest transition is destroyed. The lowest basically is like survival of the fittest. Yeah, the one with the lowest transition will be disintegrated. Maybe you may not do it every step, but you can do it every X steps. Then that will like sort of simulate a decay.
Yeah, I think the memory decay also throws out chunks quite.
Yeah, no, one thing I don't
nicely.
like about memory decay is that you need to keep computing your decay every step, which can take up a lot of compute. Yeah, I mean, it might work. Yeah, it might work as well. Yeah, you can also do memory decay. But I think if you do this, because you mentioned about forgetting, if you do it online, plus you add forgetting, then you will have something that will resemble adaptive learning. And then, the problem of the knowledge not being able to transfer to some new domain, right?
Yeah.
I think that will be sort of mitigated a bit by this. But I don't think it will win a naive structure, because like if you start from scratch on a different context, you will definitely probably learn faster. But it's interesting. So this one, sorry I went so much in detail because I think this is one of my favorite kind of architectures, that if it can learn the whole chunking online with the new with just the new like input, I think I think this is more biologically plausible.
Yeah, I'm glad you guys like it, because it's a lot of, or it's like, yes, it's hard to convince people that
I think what we need to work on next is how to abstract it such that you have as few basic units as possible. Like, for the English language, you maybe have only 26 letters, or if you add in all your Unicode characters, maybe you only have 256 Unicode characters. But like for vision, you need to compress it such that your basic unit of representation, it cannot be this 256 by 256 by 256. It cannot be a it cannot be this number. It's too big. You need to compress it more, like compress it maybe to a scale of 8, maybe. Yeah.
Yes.
So, you know, actually the human mind in image, right? It actually uses brightness a lot. Like it contrasts with the neighboring pixels. So like if you see a shadow, you expect the area to be darker. That's why we have illusions like one gray square and another gray square, actually same color, but because one is under a shadow, the shadow appears darker than the. I don't know if you see that illusion of the two tiles, gray tiles, and then one cylinder in the center that cast shadow over.
Actually, we're studying this phenomenon at the moment. So we're doing an experiment to see how people perceive visual structures and what sort of algorithm can simulate what they're doing.
So I think at the basic chunks of human vision, it is not at the pixel level. It has something to do with the contrast between pixels and like some brightness. Yeah, it's always, if evolution has something to tell us, it's always a competition. So it's like a competition between light and dark, competition between yellow and blue. You know, to me, that at least that's what I see as the basic input units. Yeah.
Because when you are not competing, then you are grouping together.
Correct. That's also why, because of the competition, like we see an image in like grayscale compared to seeing an image in color, we can recognize both images because the level of competition is the same. Yeah. So a lot of times when you do like image, you like do some change of pixel intensity a little bit, then you cannot recognize anymore. That's because the CNN structure, the base units, we need to use some form of competition-based, contrast-based metric or base unit. So the base unit, might not be a single pixel. The base unit might be the contrast of one pixel with the neighboring ones. Yeah. Anyway, this can be discussed in maybe next time when I talk about the YOLO model or something, we can talk more about the vision thing, because I disagree a lot with using pixels as vision representation.
So Xavier was suggesting that you just take an edge extractor, which I think that is also one of the things I keep seeing. Like, why don't you just extract the edges and then use it to train CNN? Then for sure, then people like the model will be tuned more to object contours rather than object textures.
I mean, if the hypothesis is that the edge contrast is the most important information, then you can try to just discard everything else, right? If that works. I don't know if that works, but if that works.
I think that should work, although I never got the time to try it.
Yeah, cool. Yeah. Anyway, I think we probably should end it soon. Yeah. I guess we more or less asked most. Sorry, I was talking a lot just now because I got a bit excited. Yeah. So
I mean, that's the best we can get, right? It's like, and if everybody is excited, then that's a good discussion.
Yeah. So anyway, I'd like to thank Shuchen again for presenting her work. This is like, I think, the base work right now. She's still trying to build on it quite a lot. And talking about how to use this for representational learning on a larger scale, that will be the next step. So I wish Shuchen all the best. We will definitely talk more offline. Yeah, I have some ideas as well. Yeah.
Yeah, sounds good. Thanks for the invitation. Yeah, I'm really glad. If it helps with your work, I'm really glad.
Oh, definitely, because abstraction is used in everything. Okay, you need to use this kind of way to learn efficiently.
Yeah, and thanks for spending the evening with this discussion group.
Yeah. So anyway, next week I thought of the topic already. Next week I will be talking about some audio processing. Like, it's basically like how a 3-second piece of audio can actually generate like the entire, like someone speaking the entire text. So it's again about representation. And then basically they use this thing called the codecs, which is like a digital way of representing it. Yeah. So I'm actually quite interested to see like how state-of-the-art models learn like and generalize fast. Actually, a lot of it has to do with this abstraction. So yeah, we can talk more about it next week. Okay? And I'll be stopping recording. Okay.
Yeah. Great. See you next week then.
See everyone next week. Bye.
Bye.